We'll be now reviewing paper 2, question 4. For this slide, I have included the deductions for the different tests. So I would like you to take out your handphone and take a photo of this table. It will be useful for the rest of the slides later. Now let me bring you through how to solve for the structure for P. So let's keep in mind this P has this molecular formula C9H10O2, and because the CH ratio is approximately 1:1, so most likely we know there might be a benzene ring that is present based on the CH ratio that is 1:1. Okay, so the most important clue that I have shown you on the left is there must be a benzaldehyde because it gives a gray PPT with Tollens reagent, which means that aldehyde is present. And for the Fehling's test, which gives no break read PPT, it indicates that there is either a ketone or a benzaldehyde. And since no phenol is present, and that it can be oxidized, so which means that it can be a primary or secondary alcohol or an aldehyde. So let's trial and error. So let's say we have a benzaldehyde, C double bond O and a H. So if you do the math, that will give you a total of 7 carbon atoms. So with that in mind, we can only have 2 more carbons to play with. And since that there is one O that's already accounted for, there must be only one more O that you can play with. And let's go with the possibility that it might be an alcohol. And this alcohol can be oxidized, so it can be a secondary or primary alcohol. And since on the left hand side there is a chiral carbon, so okay, so then the chiral carbon will be this one. So that is the structure for P. Let me bring you through how to solve for Q. Again, let's start by writing down the molecular formula C9H10O2. So the first thing I will draw is the phenol functional group because it gives a purple complex with neutral FeCl3aq. So a phenol already accounted for 6 carbon atoms. So please bear in mind that there are 3 other carbon atoms that you can put in. So since I know there is no CC double bond, and based on the Fehling's test and the Tollens test, you should have an aliphatic aldehyde. So aliphatic aldehyde, and since it can be oxidized, so I already have one O that is already accounted for by the phenol. So then the other O will be due to the aldehyde. So, and there must be a chiral carbon. So it will be like this. Okay, and then this is the chiral carbon. So that is the structure for Q. Now we will solve for R. Again, we will write down the molecular formula C9H10O2. We already know that there is a phenol, so let's draw out the phenol. And the phenol will account for 6 carbon atoms, which means you have 3 more carbon atoms to play with. And one very important thing is that the Tollens test shows that it's not an aldehyde, and there is no break rate PPT with Fehling's test. So which means that it might be a benzaldehyde or a ketone. So let's go with a ketone, which I'll circle in red. So with that, right, let's say there is a ketone, and we know there is no chiral carbon. So let's draw out. So let's say I have a ketone here. Then I have only accounted for 1 more carbon. I left with 2 more carbon, so it might be like this. Okay, and there is indeed no chiral carbon. Another possible answer is there is a phenol, but I will place my ketone further away. So this is 2 possible answers for these are the 2 possible answers for R. Let's now solve for the last compound S. I again will write down the molecular formula C9H10O2. So we know there is a phenol. So let's draw out the phenol. I have 3 more carbon atoms to play with. I know there is a CC double bond. And one more thing is that it does not give a positive Tollens test. That means there is no aldehyde. And also a negative Fehling's test, which means it can either be a ketone or a benzaldehyde. But benzaldehyde we can eliminate because we already know it's not an aldehyde. Can it possibly be a ketone? No, it cannot be a ketone because if it's a ketone, it doesn't a ketone cannot be oxidized. So, but the deduction on the left shows that it can be oxidized. So since we already know that it's not an aldehyde, it can never be a ketone, so it must be an alcohol. And this alcohol must be, most likely, it must be bonded to a carbon that is chiral. Okay, so we already know there is also a CC double bond. So with that, let us try to draw out the structure. So I know there is an alcohol, okay, and it must be chiral, so it must be a CC double bond. And I only have 3 more atoms to play with, so it should be like this, okay. And this will be the structure for S. Now for question 4b, isomer Q, if you remember, isomer Q has a phenol functional group. So they ask, why is isomer Q soluble in aqueous NaOH? So the first thing I must see that you must tell me that this phenol functional group will react with aqueous sodium hydroxide via a acid-base reaction. So the acid-base reaction will produce something called a phenoxide anion. And for A levels, when they ask a solubility question, and you must answer it in terms of energy compensation. So you must answer it in the form that the energy released when the phenoxide anion interact with the polar water molecules via ion dipole interactions is more than enough to compensate the energy that is required to overcome the hydrogen bonds between the water molecules. Okay, so that will give you your 2 marks. Now for question 4C part 1, you need to take a good look at the diagram and also a few keywords that I've highlighted in video. The first one is fuel cell. In a fuel cell, the fuel is being oxidized. So what is happening is the fuel should always be found at the anode. And in a fuel cell, the O2 gas is the one being reduced. So it should be at the cathode. And later, when you form the half equations for anode and cathode, both of them will combine to give an overall combustion reaction. Okay, combustion reaction. Okay, and why do I say you need to deduce the clues from the diagram? Because if you take a look for the electrode compartment on the right hand side, O2 and CO2 are supplied, and then what is the output? Excess O2 and CO2. What they are trying to hint to you is that O2 and CO2 are the reactants. Okay, for the electrode on the left hand side, H2 is being supplied. So H2 is the reactant. And what is coming out is CO2 and H2O are produced. So they are the products. Okay, so if you can piece together these clues, right, and also with the clues that CO3 2 minus are produced and used up at the cathode and anode respectively. So for the electrode compartment on the right hand side, half O2 plus CO2 will give you CO3 2 minus. Okay, and then because you realize that there is 2 minus charge on the right hand side, then in order to balance the charge, it must be plus 2e minus. Therefore, the compartment on the right hand side is the cathode, where reduction occurs. And then for the electrode compartment on the left hand side, we know that H2 gas is the reactant, CO2 and H2O are produced, and we know that CO3 2 minus is somehow involved, and if you put the CO3 2 minus on the left hand side, everything balances out nicely. And so in order to balance the charge, I must put 2e minus on the right hand side. So the anode is where oxidation occurs, and therefore the electron flow is what I have shown. Okay, moving from the cathode to the moving from the anode into the cathode, which is from left to right through the external wires. Okay, so coming back to the overall equation, the overall equation should be that hydrogen gas is the fuel. So if you are sharp, you cancel out the 2E minus and the 2E minus and the CO3 2 minus and the CO3 2 minus. The overall equation will be the combustion reaction of hydrogen gas. And when hydrogen gas is combusted, you give you water. This is another question on fuel cell. So the fuel cell that we are referring to here involves HCOOH. So the HCOOH is the fuel. So from the phrase fuel cell, we know that at the cathode, oxygen gas is being reduced. And since they tell you that this is carried out in aqueous acid, so the correct half equation that you should pick out from the data booklet is O2 plus 4H plus 4E minus give you 2H2O. And E cell is calculated using the formula E naught reduction minus E naught oxidation, which gives you 1.23 minus 0.61 volt. And the final answer is plus 1.84 volts. Okay, so a fuel cell is a galvanic cell and it is a positive E naught cell value. For the other question is a qualitative question. They ask you how will the cell EMF change when the pressure of CO2 is increased. So when you phrase your answer, it's important to refer to the correct half equation. So when your CO2 pressure is increased means the reduction of CO2 becomes more favorable, which means the E cell that involves CO2 reduction become more positive. Okay, so if you refer to the E cell calculation, the reduction of O2 there is no change, so same minus something that is more positive, the new E cell value will become less positive. Now 4E is a recall question. I asked for 3 basic assumptions. So you should give the 3 most important ones. I think most of you know the 2 most important ones. I will tell you some of the BOD I gave for some of you. So the first one is some of you wrote the ideal gas have negligible volume as compared to the volume of the container. I actually gave you correct, but the more correct one is you should put in the word particles. Okay. The particles of an ideal gas has negligible volume as compared to the volume of the container. Remember, to play safe, you should put particles. Then the second most important one is between the gaseous particles, there in an ideal gas, there should be negligible forces of attraction. The last one that some of you do not know is that the collisions between the particles of an ideal gas are perfectly elastic. Some of you are very detailed. They say the collisions between the ideal gas particles as well as the collision between the ideal gas and the walls of the containers are perfectly elastic. That is actually the more correct version. But I must definitely see perfectly elastic. Now for the last part of question 4, because it is a 1 mark question, so we are not very demanding in terms of the answer because we will accept 2 possible versions of the answer that explain why. If you look at the diagram, SO2, the deviation from the horizontal line of an ideal gas is more. So the first thing I should see is that SO2 will deviate more from ideal gas behavior as compared to CO2. So why does SO2 deviate more? There are 2 possible explanations because it's a 1 mark question. So you can point out that SO2 is a polar molecule while CO2 is a non-polar molecule. So the PD-PD forces between SO2 molecules are stronger than the weaker ID-ID forces between CO2 molecules. The other possible explanation is that you go and calculate the molar mass of SO2 as well as a CO2. So you tell me that SO2 being a larger molecule, it has a larger and more polarizable electron cloud, or it contains more electrons. This will give rise to stronger ID-ID forces between SO2 molecules as compared to the ID-ID forces between CO2 molecules. Okay, because like in the previous part, one of the important assumptions for ideal gas behavior is that there should be negligible forces of attraction. Okay, so that will be the last part of question 4.